Welcome, everyone. It's my pleasure to introduce today Dr. Jiang, who is a colleague of mine here a couple of doors down my hallway at the University of Canterbury. Ke is an expert on high-performance metallic and composite structures. Her interests include stainless steel, FRP, 3D printing of metallic structures. She completed her Master's of Science at Imperial College in London, and then she went on to get a PhD at NTU in Singapore. And now she's with us, and we're very happy to have her here. She's received several awards, including the Women in Engineering, Science and Technology Award in 2023 in Singapore. She does numerical work, she does experimental testing, and she also works on design approaches. Ke is going to talk today about a large test that was done as part of what we call DT2, Disciplinary Theme 2. And as you will see, the test was a big enterprise that involved many people. In my mind, the test and the data that were produced are a great opportunity to collaborate, share not only the data, but the lessons that we learned. And in my mind, that's the main purpose of QuakeCoRE. So this is a very exciting seminar for me. So with that, Ke, I should remind people before that, I'm sorry, Ke. If you have questions, please type them on the chat for now. We'll have a few minutes for questions at the end. And don't forget to mute your microphones. Okay, so with that, Ke, please.
Thank you, Santiago, for your introduction. I'm Ke Jiang, from a lecturer in structural engineering at University of Canterbury. And today I'm going to talk about this large-scale test finished this year, May, in Taiwan. It's a collaborative project, a shake table test on a hybrid steel reinforced concrete wall building. So I'll start from some introduction of the background of this test, and then I will introduce the building we test in Taiwan, and then discuss some preliminary results from both structural side and the non-structural side. So firstly, introduction. As Santiago mentioned, yes, it is a collaborative project involved for many people's efforts, and it is a large group of people who has contributed to this test. Fu Pei is the leader from NCREE side, and Santiago Puju happened to be the chair of this seminar, is the leader from New Zealand side. And not only these people, we actually got many help from both technicians and students in Taiwan. This team efforts to make this thing come true. The background, the idea of DT2 is to study the whole of building seismic performance. We have investigated the component levels performance of different components like beams, columns, braces, diaphragms, core walls. But DT2 is the opportunity to integrate all these efforts together and to study the interaction among components and to study the whole of building seismic performance. That's the initiative of the this shake table test on the hybrid steel reinforced concrete wall building. And the scope of this particular large-scale test is to quantify the drift in a steel concrete hybrid building and to quantify the drift for a very irregular building. As you can tell from the previous photos and the schematic diagram, this building is quite irregular. And to study the interaction among different components, including both the structural components and the non-structural components. The final goal is to make a building that can be reused quickly by limiting drift and so-called wisely selecting non-structural component. So that's the scopes of this test. Then I'll show you how this building looks like. It is a 5-story building, and it is a scaled building, 2/3 scale down from the real building. And the story height is 2.5 meter. Besides, the first story is actually 2.7 meter. And the plan dimension is 5 meter by 5 meter from both north-south direction and the east-west direction. And we will always be curious to see what is the lateral load resisting system of this building. Along the north-south direction, the lateral load resisting system is mainly contributed by this concrete core wall. There's two C-shaped core wall and linked by several coupling beams. That is the main contributor for the lateral load resisting in north-south direction. For the east-west direction, the lateral load resisting system is also comes from this core wall. But besides that, we also have connections at top north facade. These are the steel moment connection, moment resisting connection. And also we have BRBs at north facade, which also help with the lateral load resisting. So that's kind of the structural layout. And for the non-structural layout, we have a different type of component at different stories. The story 2 and story 3 are the New Zealand interest, and the story 4 and the story 5 are our Taiwanese friends' interest. And we actually investigate we actually put curtain walls, partitions, ceilings, sprinkles on story 2 and story 3, and for story 4 and 5 are the veneer and the bookshelves. You will have more details in the following slides. The project start this year, March. We start to assemble our building in the NCREE Tainan lab. Because this building is quite huge, so actually we separate into 3 pieces and lift them to the shake table and assemble them one by one. Yeah. And after that, in April, we start to construct a non-structural element and also do our instrumentation. And the whole test start from end of April to May. It's about 2 or 3 weeks. And after the demolish, we start our analysis of the result start from actually day 1 of our testing. And this is still ongoing because we have a data mountain. So as Santiago just mentioned, yes, we are welcome to any form of collaborations if we want to look at the data, if we want to collaborate in a way of propose new method or do more analyze, you're welcome to contact us. So our test include 3 phases. The first phase includes 8 rounds of shake, use a central goal motion, and the intensity is up to 0.5, means 50% of the intensity. Then phase 2, we put our BRBs on and run more shakes, and the intensity is up to 150%. And the phase 3, we take down the BRB and replaced with some more non-structural element, curtain walls. but the structure configuration will then become the same as phase 1. We run another 10 runs, and also including the other runs, other 6 runs using different ground motions like the Chichi earthquake or the Christchurch earthquake. There's 42 runs in total. Then I want to briefly discuss some preliminary result on the structure component. To start with, I want to show a video of the largest, the round 42 with the largest drift. The shake is in both directions, east, west, and north, south. And the intensity is 150%. There's no BRB. The max roof drift ratio is up to 2.6% at the roof. So I think you are quite convinced that yes, we actually induced a heavy earthquake, and during the shaking, you can see some torsion performance of the building. Okay. Yes, we run many runs, many shakes, and we induced a very heavy intensity. But even with that, actually very minor damage to structural element were observed. Specifically for like concrete core wall at the end, this is a photo of the cracking map of concrete core wall at the end. And as you can see, there's no corrosion of concrete, or there's no wide cracks on the concrete core wall. So we can see the concrete core wall at the end of the test is in a quite good shape. However, there's some minor damage to the coupling beam. As we know, the coupling beam is quite susceptible to drift. Even with that, the coupling beam was quite okay up to very large drift until round 24, which is bidirectional shaking and with intensity of 150%. We observed some shear cracks on the coupling beam, but then we use a very simple way to repair it, just some steel plates and anchored. And it works. Just to show the round 24 where the coupling beam has the shear crack, and these the third story's coupling beam is the one that having crack. Yeah, now you can see there's some cracks on the coupling beam now. But again, it is at a very high intensity, heavy shaking, and a relatively very large drift when the coupling beam got damaged. Okay. And for the steel component, there's not much damage or failure, or there's no damage or failure observed. Still BRBs and gusset plates, columns, beams, connections, they are all in quite good shape at the end. We only see some yielding near the end of the column base, and those yielding cannot even be observed. We need to look really into the string data to see, oh, okay, there's some yielding at the column base. Yeah. So in general, all the steel components, they are all good. And for the diaphragms, As you can see from this figure, the red lines are the cracks that are observed before testing, and the black ones are the cracks observed after testing. It is quite obvious that the diaphragms were all in very excellent shape at the end of the day. And so we can kind of conclude that the cast in place diaphragm are quite robust and dependable. And designing them are actually not so hard. We just design them according to some strand time assumption, just like our industry did. Okay, so besides damage, I also want to show some numbers. Here are four figures with the roof drift plot against the PGVs. In both, the top two are for the north-south direction, and the bottom two are for the east-west direction. Here you can actually see there's a roughly linear relationship between the roof drift and the PGV. Yeah, we did see some outlier, but basically they are quite linear. And in the east and west direction, you can see two different group of linear relationship. That is for the group of rungs with BRB and without BRB. And there's another quite interesting result we found, that is for the repeated test. Run A, this figure plot run A and run B's roof drift ratio. Run A and run B means two runs with the same intensity. So in general, they are aligned well with each other. We can in general see the repeated test here actually give a quite similar roof drift ratios in run A and run B. And for the drift ratio, for the small drift ratio, smaller than 0.5%, ratio between run B and run A is a bit large. At the initial stage, that is because for the run A's, the building is quite in a perfect shape, and at run B, there's some cracks formed on the building, so it lost some stiffness. But when the drift ratio is larger than 0.5%, the average between roof drift ratio of run B and run A is about 1.1, and yeah, and this line means y is equal to x. The roof drift of run B and run A is equal to each other. So actually from the figure, we can kind of conclude that for the repairing of cracks, should we really bother with repairing of many cracks? Probably the answer is not really. So, yeah. Then the next part, I want to show some preliminary result of our non-structural element performance. For the non-structure at the second story, yeah, we put some for the partition wall at the second story. There's two rooms, and for each room we have different detailings. Actually, for the one of the room we use a conventional detailing for the partition walls, and for the other room we use so-called advanced or low damage detailing for the partition walls. For the second story, that is the cubic, and for the third story, that's AWCI detailing. And for the curtain wall, we consider both a single corner panel and individual panels of curtain walls. And then this is how a curtain wall looks like. For the ceilings, there's both fixed ceilings and floating ceilings at the middle. And for the sprinkles, we have the pipes And we have the droppers, both rigid droppers and flexible droppers. There's an interesting video produced by one of our sponsors, and it's about the non-structural element performance. Those photos show the detailings of connection. Yeah, so basically you can see a lot of the detailings and how they are performed during the real shaking in these videos. And specifically for each component, basically for the sprinkles and the sealing, they did very well. And probably the reason is the scale. And but however, for the partition walls, although we did make a lot of efforts to improve the partition walls performance, like introduce a lot of low damage details, and however, the performance of the partition walls are not that good as expected. They got damaged as drift increase. One of the important indicator is the number of screw popped out. Here in the photo, you can see the markers on the partition walls that indicate the popped out screws. And here in the figures, you can see the relationship. We plot the number of popped screws against the storage of the ratio. So after the storage of the ratio reached the 0.5, before 0.5, there's not much, there's no popped out screws. And between 0.5 to 1%, this number of popped out screws is kind of reasonable and not too bad. But after 1% roof storage of the ratio, the number of popped screws just dramatically increased. And for the curtain wall performance is quite good. In the other hand, and you can see there's some good detailings that really work and help the curtain wall remain low damage or no damage after shaking. And for the bookshelf, books are one of the most attractive gambling game actually when we were doing test. We are guessing how many books dropped during after each round of shake. So this and the reason why we can gamble around the number of book drop is because the performance of books are quite that they are not predictable, they are unpredictable. Like for example, if we compare those two rounds, round 21 and round 29, both with 100% intensity, one is with BRB, one is without BRBs. That leads to the difference of the floor acceleration. And also for round 21, there's no connection between bookshelf and the slab. And in round 29, there's a connection, and this bracket connection is something look like this. But as you can tell from the photo, actually the number of book drop is roughly same or similar. So we at this stage we say there's no clear correlation between the number of book drop and the bookshelf performance with the acceleration drift or the good or bad connection. Just before I finish, there's some takeaway points, highlight the preliminary result of this test, some lessons learned. For the structural component, although the building is quite irregular and it is a hybrid steel concrete building, which is relatively a bit complex, and although we run many rounds, we run many shaking during the testing, and although the intensity of the shaking is quite high, there's a heavy shaking comparing to what we used for our design, but the structural components, they performed really well. There's only very minor damage, and it is at the very late stage. However, for the non-structural element, there's some damage still observed for the partition walls, but this damage was kind of under control when the drift is limited to like 0.5 to 1%. The drift here means the interstory drift. And so we can conclude that we can actually indeed make a building where everything can work well if we really control the drift and we wisely select the non-structural element and make sure their connection to structure are good. I think that's the end of my presentation, and here I want to thank NCREE and the QuakeCoRE for the support of this project, and there's also sponsors for our non-structural elements. Thank you, and thank you for attending this seminar.
Thank you, Ka. That's an excellent summary of a very large test that involved 3 years of planning and a lot of people. I also want to mention that Ka worked very hard, and not only her did so. As she showed at the beginning, there were many people involved in this. I think a special mention is due to Alex Shige, because he worked extremely hard to coordinate among all these sponsors and get everything lined up to set up and test all the non-structural components that were tested. He worked extremely hard, and he really went the extra mile in this test. I think, because you said there were so many names, to try to mention them all, it's always risky because we'll probably miss some, but I think your student Alejandro Sainz also did a lot of very good work. He spent 2 months or maybe 3 months in Taiwan.
Yeah.
So that needs to be acknowledged too. There were people like Julian Rincon, who took vacation time to help in the testing, which was quite amazing. Also, a visiting scholar here at UC, Dr. Susumu Takahashi, used a lot of his sabbatical time generously to help with the project. Rick Henry was very much instrumental in the whole conceptual design. So many people. Moshtaba Hosseini, who's a student of Alex's, put a lot of time and effort into this, and so did a postdoc who's no longer with us, Dr. Will Polalis. Rajesh Taka, the work